All right, so continuing with the right triangle definition of the trig functions. So you'll remember that in section 4.2, we talked quite a bit about pi over 4. And in fact, we figured out that with the unit circle definition, the sine of pi over 4 was square root of 2 over 2. And the cosine of pi over 4 was square root of 2 over 2. We figured all that out. So what we're doing now is seeing how that works for the right triangle definition. Hopefully it works the same way, or at least gives you the same result. So I want to start off by telling you a little about this. So if you make a right triangle with a 45-degree angle, well, you know that the angles of a right triangle, of any triangle, have to add up to 180 degrees. Which means this angle over here will also be 45 degrees, right? So there's a 90, there's a 45, there's a 45. So if your triangle has two equal angles, it also has to have two equal sides. So let's suppose that the lengths of those two equal sides are 1, and I want you to pretend for just a minute that this is not here. Just ignore that. Because I want to actually figure out why is that what it is. Okay, so I'm going to put my, let's see, grab my pen here. Okay. All right. So let's say instead of, well, let's pretend I don't know what that is, and I'll just call it C. So by the Pythagorean theorem, one squared plus 1 squared has to equal c squared. 1 squared is 1, 1 squared is 1, 1 plus 1 is 2. So that means c squared is 2. And if c squared is 2, of course, that means c has to be the square root of 2. So that's how they got that this was square root of 2. Okay. So now let's uncover that. All right. Okay, so using our right triangle definition, here is our 45-degree angle right here. So if I want to know, for example, the sine of 45 degrees using this definition, I would say the opposite over the hypotenuse. The opposite is 1. The hypotenuse is square root of 2. So that means, for example, and I believe you'll see this all on the next slide. That means, for example, that the sine of 45 degrees is 1 over the square root of 2, okay? And I've told you before, I am personally not super picky about rationalizing denominators, but for example, my math lab is. And so whenever they ask you anything about the sine of 45 degrees, you have to change that to square root of 2 over 2, right? Okay. All right, so now we have this example. Using that same triangle that we were just working with, we're going to find the cosecant, the secant, and the cotangent of 45 degrees. Now, SOHCAHTOA, some old hippies came around here tripping on acid, is only for sine, cosine, and tangent. It does not help you with cosecant, secant, and cotangent. So for those, you really have to remember, or at least the way I like to remember it is the cosecant is the reciprocal of the sine. Secant is the reciprocal of the cosine, and the cotangent is the reciprocal of the tangent, right? Okay, so let's see how they do this. I might add some of my own scribble to this. Okay, they did it a little differently. So they used, okay, so sine is opposite over hypotenuse. So they're flipping this over. This is the reciprocal. Instead of opposite over hypotenuse, it's hypotenuse over opposite. So I think I will add just one little thing to this that I hope is helpful. Over, I guess over here, I'm just going to remind you that the cosecant is the reciprocal of the sine. So sine is opposite over hypotenuse. Cosecant has to be hypotenuse over opposite. Okay. All right, and then the secant is the reciprocal of the cosine. Cosine is adjacent over hypotenuse, so secant is going to be hypotenuse over adjacent. Okay, so that's exactly what they have there. And that comes out to the same thing, right? Because the opposite is 1, the adjacent is also 1. Okay, that's only going to happen in a 45, 90 triangle, that the opposite and the adjacent will be the same. Okay. And then the cotangent is the reciprocal of the tangent. Tangent is opposite over adjacent. Cotangent's got to be adjacent over opposite. So let me put that in there. This is the reciprocal. Whoops, sorry. Forgot to switch it back to pen. Okay. So this is the reciprocal of cosine. And this is the reciprocal of tangent. All right, so that brings us to 30 degrees and 60 degrees, aka pi over 6 and pi over 3. So of course, let's see. An equilateral triangle is the only kind of triangle that has 3 60-degree angles. So I'm talking about this big triangle. Imagine this big triangle is equilateral. So it has 3 equal sides and 3 equal angles, and those angles would all have to be 60 degrees. So now in order to get the 30-degree angle in there, I am going to cut that big triangle in half. Okay. All right, now remember, you can make these triangles any size you want. I remember telling you, I think it was in the last section, or maybe it was at the beginning of this section. It was at the beginning of this section, that the values of the sine and cosine and all the other trig functions depend only on the size of the angles and not on the size of the triangle. Okay, so you could make these 3 equal sides anything you want. We're going to make them 2. And the reason for choosing 2 is because when I cut this triangle in half, then half of that will be 1. All right. I mean, I could have made this 1 here if I really wanted to, but then I would have been into fractions, and that makes things a little messy. Okay. All right. So we start with our equilateral triangle with all sides equal to 2, and then we cut it in half, which makes this side 1. And now pretend once again that you don't see this. All right, the reason that's what it is because, again, of the Pythagorean theorem. So if I call this B, then by the Pythagorean theorem, 1 squared plus B squared has to equal C squared. 1 squared is 1. B squared is B squared. Oh, I made a mistake. That was supposed to be a 2. I already know C is 2. Okay, 2 squared is 4. Okay. So I have 1 plus B squared is equal to 4. And now if I solve that equation for B, I'll subtract 1 on both sides. That'll give me B squared equals 3. And if B squared equals 3, that must mean that B is the square root of 3. Okay. So now I can uncover this. All right, so now that we know all 3 sides of this right triangle, we can evaluate any trig function at 30 degrees or 60 degrees. So they're asking me to do tangent 60 degrees to start off with. So here is the 60-degree angle. The tangent is the opposite over the adjacent, right? So here is the opposite, square root of 3. Here's the adjacent, 1. So that's how we get the opposite is square root of 3, the adjacent is 1, and of course the square root of 3 divided by 1 is just the square root of 3. Okay. And then for 30 degrees is up here. So now the opposite and the adjacent, they flip, right? Now the opposite is 1 and the adjacent is square root of 3. So the tangent of 30 degrees is going to be 1 over the square root of 3. And 1 over the square root of 3 for people who are picky about these things, like my math lab. To rationalize the denominator of 1 over the square root of 3, you have to multiply the top and the bottom by square root of 3. And you get that the tangent of 30 degrees is square root of 3 over 3. Tangent of 60 degrees is square root of 3. All right, so now that we've talked about pi over 4, aka 45 degrees, and we've talked about pi over 6 and pi over 3, we actually know, we've already figured out some of these, and the others we can pretty easily figure out. We now know how to find the sine, the cosine, and the tangent of pi over 6, pi over 4, and pi over 3. So let me see if I can remember which ones of these have we actually done. I remember scribbling this one for you on that other slide. And then we just figured out this and this. Okay. All right. So again, using SOHCAHTOA, you can figure out any of these others. So there are some cool patterns to this. For example, if you look at sine, everything is over 2, and upstairs it goes from 1 to square root of 2 to square root of 3. And then when you look at cosine, it's exactly the same values run in reverse. Square root of 3, square root of 2, and 1. You could even put the square root over this 1 if you really wanted to. It makes the pattern a little more clear, right? If you wanted to. Sine, I'm sorry, tangent is a little bit not as obvious of a pattern. So the way that I recommend remembering your tangent values, I mean, eventually, hopefully you'll have at least these 3 memorized. But in the meantime, just remember, well, you can do it one of 2 ways. You can either do the tangent as the opposite over the adjacent, or you can do the tangent as the sine over the cosine. Either one of those will work.